We have seen in our earlier lectures how Ampere's law can be used to find the value of B bar in symmetrical situations. And the types of symmetrical situations that we either discussed or we pointed out, those situations were as follows. One symmetrical situation where Ampere's law is useful is the situation of infinite straight lines. There's another situation which we just noted, the situation of infinite planes. The third one is of infinite solenoids, and the fourth situation is that of toroids. Now when we say that Ampere's law is useful in finding B bar in these symmetrical situations, it doesn't mean that Ampere's law is not applicable in other situations. Remember, Ampere's law is a law which is always applicable. It's a very fundamental law of electromagnetism. On the other hand, although always applicable, it's not always useful to find the value of B bar. In situations of symmetry, such as these four situations which are mentioned above, in these and similar situations, if we find B bar using Ampere's law, we can rapidly find the answer. Probably it is much more rapidly as compared to Biot-Savart's law. So that's why when we discuss Ampere's law and the applications of Ampere's law, we usually confine ourselves to the discussion of these four types of symmetries. Now in the class we have already covered infinite lines, infinite or long solenoids, and toroids. And the one situation that we did not do in class and which I will cover in this particular screencast lecture is the situation of infinite planes. So we will try to find B bar in an infinite plane of current. First of all, let us be clear as to what exactly we are talking about. We want to find B bar due to a current carrying infinite plane. It's a plane in which current is flowing. So for example, if you consider your computer screen as a part of the plane, so all this is a part of the plane, and of course the plane extends infinitely in all these directions, infinitely down and also infinitely in that direction. So that's a plane. And secondly, a plane doesn't have any thickness in the direction perpendicular to the computer screen. So that's what I mean by a plane. It is this particular region which is going to carry a current. Now how is the current flowing? Imagine that the current is flowing from bottom to top on your computer screen. These red lines signify the flow of charge or current. And further assume that the current is uniformly distributed all over the plane. In other words, if I take a length, let's say L here, and I find what is the current which is passing across this length, and I take the same length perpendicular to the current in another region of the plane, then I'll find that the same amount of current crosses this line segment of length L. It's a line segment, okay? Same amount of current passes in this region as well as in this region. That's what I mean by uniformly distributed current. Now another thing you must recall is that when we said a plane, we really meant an infinite plane. So these lines, they don't really stop here, they go right up till the extreme right hand side, in fact up to infinity, and this side also up to an infinite distance the current continues. And if you go down an infinite distance, you'll still see the current flowing, as well as if you go up, you'll see the current flowing. So that's what I mean by a current carrying infinite plane. Of course, I should have used the word, I should have specified assuming uniform distribution of current. Another way to visualize this infinite plane of current is to imagine that current is flowing along the floor. This thing which you have drawn over here, it may be like the ground or the floor. So it's flowing like a river. Current is flowing like a river, and the only thing is that the river has infinite breadth and infinite length, and it has zero thickness. So the water or the current which is flowing doesn't have any thickness perpendicular to the plane of the screen. So that's another way you could visualize what do I mean by a current carrying infinite plane. Now, as you know, when current flows, it generates a magnetic field, and so we are about to find what is the magnetic field generated by this infinite plane which carries uniformly distributed current. For that, I'll draw the diagram of this particular river of current, but from the viewpoint of an observer who is situated in the plane itself. So you can just imagine that the observer is over here, and the observer is looking at the current which is flowing away from him. So what he will see is the following diagram. So each of these crosses which I have marked here within circles represents current which is flowing away from the observer, and this is the side view of the plane actually, and therefore you don't see any thickness at all. The thickness would be this thickness. It's equal to 0 because it's a plane, and being a plane, I have drawn these dotted lines which signify that these arrows can be drawn right up till infinity because the plane has infinite width. So that's the picture that that particular observer would see. Now just ask the observer to describe the current which is flowing away from him. He is not going to tell you what is the value of the current, because if you sum all of these currents flowing away from the observer, it's going to be infinity. A better approach would be to imagine some length L which is perpendicular to the flow of the current. Find out what is the current, let's say I, which flows only in this region, not counting the current which is flowing in these regions, for example. Now that's a finite current because L is finite, and then he can calculate what is the current density. Now by current density, what I mean is the linear current density, which I define to be measured in amperes per meter rather than in amperes per meter square. So that's going to be the current I divided by L. Now if you go to the previous diagram, what it would mean that the observer has identified a region or a line. He has drawn a line segment, let's say, and this line segment which he has drawn is perpendicular to the flow of the current. Its length is L. So what he is measuring actually is the current which is flowing across this line, and that's what I call I, and the linear current density is then I divided by L, and naturally I is in amperes, L is in meters, so the linear current density is in amperes per meter. So he does that, and that is how he will actually describe to us the value of the current. He won't describe the current, he won't say what is the current, he will say the current density. The current density is I by L, and that current density is the same irrespective of where you take this L. You could take the L here or here. The current being uniformly distributed all over the plane, the linear current density is a constant, and that constant I'll call K. So if I have a plane carrying current of uniform density, linear current density being equal to K, then the question is, what is the magnetic field which this particular current distribution generates? Okay, so what I'll do first is to create a bit of space by moving this sentence down like that. And now just imagine I want to find what is the magnetic field, let us say at a point P, which is situated over here. Now the symmetry suggests that at least we can give Ampere's law a try. But before applying Ampere's law, it's often useful to guess what is the direction of the magnetic field at the given point. So let's try to do that. The point P is directly above a certain line of current, namely this one, and it's an infinite line of current, and you can apply the right hand rule to draw or to visualize the magnetic field lines which are generated by this particular line. There will be a set of concentric circles in the plane of the computer screen, in which incidentally point P is located, and the lines will go something like this, such that the magnetic field due to this particular line of current at point P must necessarily be towards the right. If I draw the field line, it's pretty clear why I'm saying that the field is towards the right at P, is tangential to the field line. So that's the entire field line. Now let's consider a line of current which is away from this one. For example, consider this particular line of current. Now if I draw a line segment joining that line to P, then once again if you apply the right hand rule, you get the direction of the magnetic field at P because of this particular line of current. The field lines are going to be concentric circles like that, this time around the line which we are considering, and surely the field at point P because of that particular line will be something like this. This angle is going to be 90 degrees. Now what I do is I take a symmetrically placed current on the right hand side. So this is the current I'm talking about. So these two currents, this current and this current, they are symmetrically placed about this central current. Now once again apply the right hand rule, and you'll see that the field lines are going to be concentric circles like that. So finally the direction of the field at point P, if I draw these circular arcs, is going to be like that. And now I think it will be obvious to some of you. What we have done is we have drawn the field because of this current and the field because of symmetrically placed current, and these two fields, you see that by symmetry they are going to make equal angles. Let's call it theta with this blue arrow, and naturally their components in the vertical direction in the computer screen, those will cancel, and when they add, those two fields, we add them, we get the total contribution to be towards the right. Now we can continue this process for other pairs of such lines. For example, if we consider this line, and likewise we consider this line. Now these lines are once again symmetrically placed about the central line of current, which is directly below P, and naturally when I draw their magnetic fields at P, they are, when I add them again, I'll get a rightward field by the same logic. So we can add the fields pairwise and you'll always end up getting a rightward contribution, and the conclusion is quite obvious. The magnetic field at P, because of the entire plane, is surely going to be towards the right. Now imagine you can draw a line, a dotted line. This distance is equal to d. Now imagine the symmetrically placed point on the other side of the plane. In other words, you go the same distance d below the plane and you'll have a symmetrically placed point which you call P dash. Now by the same logic you can prove that the total magnetic field, the resultant magnetic field at P dash, because of this entire plane of current, must be towards the left. Not only that, if the field here has a magnitude B, then the field here too has a magnitude B, and that's by symmetry, because we have taken these distances to be equal. Now I will exploit this particular symmetry as well as the directions of B bar to find B by Ampere's law. So what we do is to draw an Amperian loop which passes through P as well as P dash, and I'll assume that that's in the form of a rectangle like this. Okay, it passes through P dash as well as through P. Now let's imagine traveling through this Amperian loop in the clockwise direction like that. The left hand side of Ampere's law is integral B bar dot dl bar. The right hand side of course is mu naught multiplied by I inside, the net current which pierces the area which is bounded by the Amperian loop. So let's try to evaluate the left hand side. The left hand side, let's say I start from point P over here. I go to Q and then R and then S and then P. I have to complete the loop. Now when I go from P to Q, if I assume that this length is L, then the contribution towards the left hand side integral which comes from PQ is going to be B multiplied by L. I want you to understand that the field here I realize that I should not have used the symbol P. I've already used it elsewhere, so maybe I'll give it some other name. I'll call it P2. Okay, so anyway, I want you to realize that the field at all of these points which I've marked by red dots, it's the same. In magnitude it's B, and in direction the field is leftward. That's because of the symmetry of the infinite plane. And likewise, if you go to RS of the rectangle, side RS, then all these dots I've drawn on that side, if you go there and find the magnetic field, everywhere the field is going to be rightward and everywhere its magnitude is going to be B. And that's why P2Q, its contribution towards the integral, is going to be B2 multiplied by L. Now when I go in this direction, remember the field is going to be perpendicular to the direction of travel. For example, before I strike the plane, the field is leftward, and after I strike it, after I get through the plane, the field is rightward, and therefore these terms b bar dot dl bar all along this particular line segment, that is from Q to R, they are all equal, each of them is equal to 0, and therefore the contribution towards the integral from side QR is equal to 0. Note that if we consider the dl bar over here, which the place where the plane actually intersects this Amperian loop, if at all there is a contribution from b bar, it's going to be negligible. It's only there for that dl bar. Now we've got a 0 contribution from this. Now from this particular side, that's RS, the contribution is going to be, by a similar logic, B multiplied by L. Remember, we are traveling rightwards and the field is also rightwards, so B into L, and just as before, the contribution of SP2 is going to be 0. Now that would mean that this integral reduces to BL coming from the lower side of the rectangle and another BL from the upper side, so is going to be twice BL. So that integration reduces to twice BL, where B is the magnitude of the field at point P as well as P dash. On the right hand side, it's mu naught multiplied by the current which cuts or penetrates the interior of the rectangle. So you have to imagine that there is a membrane which is spread over this area whose boundary is the rectangle, and then the current which is penetrating that particular membrane is of course this current. Now by the right hand rule, when you apply it to the Amperian loop, remember we have traversed the Amperian loop in the clockwise direction, so by the right hand rule, this current, because it goes into the plane of the computer screen, it must be treated as positive. So if this total current, let's say it's equal to I, then on the right hand side I've got mu naught multiplied by that current I, and then the value of B, I want to find B, remember, at point P as well as at point P dash is going to be mu naught divided by 2 multiplied by I divided by L, and I divided by L, we have defined it to be the linear current density. It is the current flowing per unit length when that length is held perpendicular to the current. So it's going to be mu naught divided by 2 multiplied by the current density K. Now that's the value, the magnitude of the magnetic field generated by an infinite plane carrying uniformly distributed current. Now what does this result mean? Let me just remove the clutter from this diagram. All these things I'll remove, so that I've just got back my plane and I've got my 2 points. Let's say P dash is over here and symmetrically placed, but on the opposite side is point P. So we have just discovered that the magnetic field, because of this plane at point P, it's of course towards the right, but its value is mu naught by 2 multiplied by the linear current density. And likewise, the magnetic field at point P dash is towards the left, but its value, its magnitude, is still mu naught K divided by 2. Now the field at this point as well as this point as well as this point, which are at the same distance from the plane, is going to be the same, that is mu naught K by 2 and towards the left. So the field vectors would look the same. That's all by symmetry. Likewise, if I evaluate the field here or here or here, these field vectors are going to look identical because they signify the field at points which are at the same distance from the plane, and because of the symmetry involved, the field is going to be the same. Now another thing that we note is that this particular formula doesn't contain the distance of the point P or P dash from the plane. It doesn't depend on this distance, which we called d. For example, if we go to double that distance from the plane and do the same derivation, we get the same formula, mu naught k by 2, and the same direction for the field. Now this has an interesting implication. It would mean that wherever you go on the bottom of the plane, that is below this plane, the field is leftward, and it's equal to mu naught k by 2 everywhere. So that can be denoted by drawing such similar or identical arrows, all of them pointing towards the left. So the field is mu naught k by 2 leftwards everywhere below the plane, and similarly above the plane it's mu naught k by 2 everywhere towards the right. So what we have got actually is a uniform field above the plane. Its value is mu naught k by 2, and it is towards the right. And below the plane, on the other hand, we have got another uniform field, but now, although its value is still mu naught k by 2, it is pointing towards the left. Now the field lines above the plane and below the plane would look as follows. So below the plane, remember, a uniform field is drawn by showing uniformly dense field lines, and they are all unidirectional. So these would be the field lines in the lower part, that is below the plane, and all of them go towards the left. The magnitude of the field, of course, is mu naught k by 2, and above the plane the field lines would once again be represented, or the field lines are going to be uniformly dense like that, and all of them would be going rightwards. So you have two uniform fields, one here and the second here. They have the same magnitude, namely mu naught into k by 2, where k is the current density, the linear current density. But the only difference in these fields is one is towards the right, the upper one, and the lower one is towards the left. Now we have seen earlier that this k, it is a quantity which is analogous to the surface charge density in electrostatics. For example, when we compared a solenoid with a parallel plate capacitor, both ideal of course, then the field inside the solenoid was given by mu naught multiplied by k, whereas the field inside the parallel plate capacitor was given by sigma divided by epsilon naught. So the idea is, a solenoid and the parallel plate capacitor are analogous devices in electrostatics, in magnetism and in electrostatics respectively. And the field in a solenoid, the magnetic field, when you write it, you write mu naught in the numerator. For a capacitor, the electric field, you write there's epsilon naught in the denominator. That's a common occurrence, you know that happens. For the solenoid, you have the linear current density in the numerator, and here electrostatics you have the surface charge density in the numerator. So the formulae are somewhat similar. Now, do you recall any electrostatic device or any configuration of charges which gives a field, a uniform field, which is analogous to this? Now by analogous I would mean k would become sigma in the numerator, mu naught would go below as epsilon, and the 2 remains as 2. So I think once I write sigma upon twice epsilon naught, you will probably remember that I'm talking about an infinite plane of charge. So if I have an infinite plane of charge like this is the side view. It looks like a line, but it's actually a plane because it's the side view. Then this plane of charge generates an electric field going away from it because they are positive charges. If they were negative charges, the field would be towards it. But the field goes away from these positive charges on both sides. And this field is uniform. This field is also uniform. And the value of the field we know to be sigma divided by twice epsilon naught here as well as here. In other words, an infinite plane of uniformly distributed current, this particular configuration of current in magnetism is similar to, is analogous to an infinite plane of uniformly distributed charge in electrostatics. The formulae look very, very similar. So you can write this derivation. You must have written it as I am talking in your classwork notebook, and the result is to be memorized. The result is also given in the handout. Now using this result, namely that the field generated by such a current configuration is mu naught k by 2, you can very easily solve equation from our textbook. So if you go to HCV and you see page 252, magnetic field due to a current, you see question number 52. So it says there are two large metal sheets and they carry surface currents as shown in the figure. So it can be seen that he is basically describing two infinite planes carrying currents. But if you look at the upper plane in the figure, you can see that current is coming towards you. That is signified by the circles with dots at the centers. And if you look at the lower plane, that signifies currents which are moving away from you. That's because the circles have crosses. So there are two planes, parallel planes, but they carry currents in opposite directions, and I'll just show that in my diagram like this. So you can see in the upper plane the currents are coming towards you, in the lower plane the currents are going away from you. Further, the question says that the current through a strip of width dl is k times dl, where k is a constant. So if you take a strip of width dl, so actually it's an infinitely long strip, of course, but the width is dl, then this current which is flowing away from you seems to be k times dl, and we are to assume that the same k is valid in the upper plane too. So if I take a width dl here, then the total current which is now flowing towards you is k times dl, the same k for the upper plane as well as the lower plane. Now if you look carefully, the current is I is equal to k times dl, or in fact it would be di is k times dl. The presence of a differential on the right hand side would mean that the current is also infinitesimal, because k is assumed to be some finite number. Now k would then be di by dl, and that's nothing but the linear current density which we talked about a few minutes ago, linear current density. So the linear current density is the same in both the planes, and of course the planes are parallel to each other. The only difference, of course, is that in the upper plane the current is coming towards you, in the lower plane it is going away from you. Now even before we read the question fully, we can easily show from our previous discussion that the field, because of the lower plane alone, is going to be leftward below that plane, and the value is going to be, so I'll just bring this into your view, mu naught k by 2. So leftward mu naught k by 2. It's a uniform field. Well, at least the contribution to the field by the lower plane is uniform. We aren't considering the upper plane yet. Now in the region above the lower plane, that is in this region as well as in this region, the field is towards the right. The field contribution by the lower plane is rightwards, and it's equal to mu naught k by 2 here as well as here, mu naught k by 2. On the other hand, if we consider the contribution towards the magnetic field by the upper plane alone, then the theory that we just discussed tells us that the field contributed by the upper plane in the region below the upper plane, so I mean this region as well as this region, is going to be in the rightward direction, and its value is going to be mu naught k by 2 here as well as here. So if you talk only about the contribution towards the field by the upper plane, well, the field contribution is uniform all in this region, and it's equal to mu naught k by 2 towards the right. On the other hand, the field contribution by the upper plane in the region above it is going to be uniform mu naught k by 2, but towards the left. Now let's read the question ahead. You have to find the magnetic field at the points P is over here, Q is somewhere in between the planes, and R is over here. Now it's very easy, this question is almost solved. Let's consider point P first. These two fields are naturally going to cancel, so the magnetic field at point P is equal to 0 bar. Now the same thing is going to happen for point R, because these two fields will cancel, so it's also the same result I get for R. BR bar is also equal to 0 bar. Now for point Q, the situation is a bit different, because these two fields, they are in the same direction, and so I have to add their magnitudes. So the field at point Q, which is in between, it could be any point in between actually, is just double of mu naught k by 2, and that's mu naught multiplied by k. Now this situation is again a bit like a parallel plate capacitor, where the field, let's say this is the positive plate carrying charge Q and this negative plate carrying charge minus Q. The field outside here as well as here, the field is 0, and the field inside is actually equal to sigma divided by epsilon naught. So it looks a bit like mu naught into k, because epsilon naught in the denominator corresponds to mu naught in the numerator, and sigma corresponds to k. So we've got a sort of analogous result, although the standard magnetic device, which is considered to be an analog of a parallel plate capacitor, is a solenoid. But you also have this sort of device which appears to have the same formulae, or rather analogous formulae to the ones in parallel plate capacitors. Now after doing this question, which of course you have to write in your classwork notebook, you must have written it already. If you haven't, then please do write. So we'll go to the next question, which is question number 55. All of these questions must be in your classwork notebook. Please make sure that you do that. Now question 55 on the same page is the following. A long solenoid is fabricated by closely winding a wire of radius 0.5 mm. So the radius of the wire is given to be 0.5 mm, and it is wound over a cylindrical non-magnetic frame. Now that would mean that the interior of the solenoid could be considered to be vacuum, so that the successive turns nearly touch each other. So a very closely or tightly wound wire, that's very close to the ideal actually. What would be the magnetic field at the center of the solenoid if the solenoid carries a current of 5 amperes? So we want B center. Now remember, inside an ideal solenoid the magnetic field is uniform, so we might as well be calculating what is B inside is the same as B center, and the formula is of course well known formula, mu naught multiplied by the current carried by the solenoid multiplied by the number of turns per unit length, or the turn density. Now we know the value of mu naught, it's 4 pi into 10 raised to minus 7 SI units, and the current carried by the solenoid is given to be 5 amperes, and the turn density N. Now to do that, if you have this solenoid like that, then all you have to do is actually consider some length L of the solenoid, find the number of turns. So these are the turns, the individual turns, there may be N turns. So N upon L is going to be the density of the turns. Just substitute that over here and we get the answer. However, finding small n is easier said than done. You have to use a bit of imagination because no data seems to be given which will directly give you the value of small n. The only data which we haven't used seems to be this information, the radius of the wire. Now that doesn't seem to be linked with small n, at least initially. The radius of the wire would be the radius of this particular wire. You know, the thickness of that wire divided by 2, of course. The thickness would be the diameter. So how can we use the radius of the wire to find small n? Now I'll just convert this to diameter first. The radius of the wire, if it is 0.5 mm, then the diameter of the wire must be equal to 1 mm. And I'll redraw this circuit in a slightly different way. So you can imagine that you take a longitudinal cut, that is in the vertical plane. You take a longitudinal cut, and that too in the vertical plane. So just cut the solenoid open, and what you'll see is something like this. You'll see one turn after another. We are going to simplify this tightly wound solenoid. We are going to assume that it's like circular loops of wire, one after another. They are just touching each other. So that's one such circular loop. It's actually cut. So you know, if I look at it from the side, the circular loop would have been like this, and what I've done is actually I've cut it. So I'll just remove this part. It becomes a semicircle, and then what I'm showing in the figure, actually in this figure, you can imagine that there is an observer over here. So he sees this semicircle, he sees it as a straight line segment, or a something which is straight, and this particular thing, the circle, he sees over here, and the second circle he sees over here. Okay, now similarly he can see the next circular coil like this. So it's an approximation because the turns are given to be tightly wound, and so we can imagine that it consists of one circular coil after another like this. So that's the sort of picture that you will see, and I will now show you how you can calculate small n, the turn density, just by knowing that the diameter of the wire is 1. It should have been millimeter, not meter. Is the diameter of the wire is 1 mm. Now let's see where the diameter is in this figure. It's this distance. This distance is 1 millimeter, as well as this distance or this distance, and so on. Now let's actually do it this way. You consider taking n turns. Now that would correspond to n circular loops in this diagram. So consider this to be the first, the second, the third, and so on, and maybe this is the nth loop. So what you're going to do is you're going to consider all of these loops. The number of loops is equal to n, and if I just knew this length, then I could divide n by L and I could get the turn density. I think it should be clear now. Each of these thicknesses is equal to 1 millimeter. That's the diameter of the wire. So that's 1 mm, and there are n such loops, one after the other, with no spacing in between. So the total length is going to be capital N multiplied by 1 millimeter, and so clearly small n, the turn density, would be capital N divided by capital N into 1 millimeter, and that is 1 turn or 1 loop per millimeter. Remember, we want SI units, so it's going to be 1000 turns per meter, and that is precisely the value which you substitute over here. So this 5 gets multiplied by 1000, and that leaves us an answer of B at the center is 2 pi multiplied by 10 raised to minus 3 Tesla. I think the whole point in this question was finding the value of small n from the diameter of the wire. So that was the tricky part in the question. Now the final question that we will do in this particular screencast lecture, it belongs to the extra classwork section. So if you look in the extra classwork sheet on electrodynamics, you see question number 7. I'll just read the question. It says a long straight wire along the z-axis carries a current I in the negative z direction. So if I assume the x and the y-axis to be like that, that is, the positive x-axis is towards the right, the positive y-axis is upwards, and the xy plane is the plane of the computer screen, then this particular inward pointing arrow, it denotes the current. The current is along the z-axis, but it travels in the negative z direction. Remember, by the right hand rule, the z-axis would come out of the computer screen. Now we want to find the magnetic field B bar. Because of this long straight wire at a point having coordinates x, y and 0. Now obviously, since the z coordinate of the point is equal to 0, we are considering a point which is in the xy plane. Now just as an example, you consider x and y both positive. So it would mean that the point in question belongs to the first quadrant, although I don't think it would really be a necessary condition. The answer wouldn't probably change if you change the quadrant, but as an example, we'll take a point. Let's say that point is over here. Its coordinates are x, y, and 0. Now let's figure out what is the direction of the magnetic field. Now you are aware that the field lines, they go in concentric circles in the xy plane around this particular wire. So if you apply the right hand rule, then the field lines would be concentric circles. Their center would be the origin and they would go around like that. So the field line passing through that particular point, it would go around like this. Now what that really means is if you draw a line segment from the origin to that point, then the field would be perpendicular to that line segment like that. That's of course because of the tangent radius perpendicularity property. Now if this distance, that is the length of this dotted line, is let's say r, then we know that the magnetic field at this point, which I'll call P, due to the long straight wire, that field has a magnitude given by mu naught multiplied by I divided by 2 pi multiplied by r. In fact, that would be the magnitude of the resultant field, provided that the rest of the circuit is infinitely distant. And this r can be found by distance formula. After all, it is the distance between the origin, which has coordinates 0, 0, 0, and the point P, which is x, y, 0. So what I get is mu naught I divided by 2 pi multiplied by square root of x square plus y square. That's the magnitude of the magnetic field. Now the question specifically asks for the magnetic field B bar, and that implies that the magnitude is only part of the answer. The magnetic field will actually be the magnitude, which we have called B, multiplied by the unit vector in the proper direction, the proper direction being this particular direction. So the question is, how do I actually find a unit vector which goes like that? It's perpendicular to the line segment of length r, and it goes in that direction. For that I can use a bit of vectors. So I'll redraw the diagram, and this time I won't show some unnecessary things. So I'll just show point P, for example, whose coordinates are x, y, 0, and I'll show the origin, and this vector OP bar, this vector is given by xi cap plus yj cap, and if you want you can write plus 0 k cap, but that's not needed. So you have this vector xi cap plus yj cap, and you may have guessed that I'm trying to find the unit vector u cap using some concepts of vectors. Now I know that this angle is a right angle, so I'll be using the concept that the dot product between two vectors which are themselves non-zero, the dot product is 0 when the angle between them is 90 degrees. So I'll draw yet another diagram where I have my x-axis and my y-axis, and I have my vector OP bar, the coordinates of P are x and y. Now assuming that x and y are in the first quadrant as I've shown them, if I'm able to find any point over here whose coordinates are, let's say, x dash and y dash, such that this particular vector, now this point I'll call p dash. If I can find some point x dash y dash such that o p dash, this vector, is perpendicular to the vector OP, and of course I want OP dash to be in the correct direction. I don't want it to be going there, so I'll have to verify that it's not just perpendicular but perpendicular in the correct direction. Now once I find this vector OP dash, if I'm able to find it, then it's a very simple procedure after that to get the unit vector in the direction of OP dash, and this unit vector is nothing but this unit vector which I've drawn in the previous figure. It has the same magnitude and it has the same direction. So the whole question is, am I able to find some x dash and y dash which will satisfy the condition that this vector must be perpendicular to this vector? Now let's see. OP dash, the vector OP dash, is nothing but x dash I cap plus y dash j cap, and this vector must be perpendicular to OP bar, which is x I cap plus y j cap. And if that is the case, then the dot product must be equal to 0, which would mean that x dash x plus y dash y is equal to 0. Now this would imply that x dash x is equal to minus y dash y, and that would also imply that the ratio x dash upon y dash is the ratio minus y divided by x. So if I could find any combination of x dash y dash satisfying this particular condition, that is the ratio of x dash and y dash is equal to the negative of the ratio of y and x, if I could find any combination of x dash and y dash, then my job is done, because once I find that combination, all I have to do is to set up the vector, namely this vector, and divide it by its own magnitude, which is root of x dash square plus y dash square, and I'll get the unit vector. So one such combination could be, for example, let us tentatively put x dash equal to minus y, and you put y dash equal to x. I'm not saying that this is correct, I'm just saying let's test it. Now the ratio of x dash and y dash is clearly equal to minus y by x, but does this actually fulfill our condition? That is, if I use these values of x dash and y dash, do they really give us a point in the fourth quadrant? That's what we need. So it doesn't seem to be doing that, because x dash is negative and y dash is positive. So this combination, remember x and y themselves are positive because the point P lies in the first quadrant, but x dash negative, y dash positive would mean point P dash is somewhere in the second quadrant, and I don't want that to happen. So maybe I've gone wrong somewhere in the sign. Now let's see. Instead of writing this equation, the right hand side as minus y upon x, I could have written it as y upon minus x. There's no difference, and in that case my tentative answer for x dash would become y, and similarly my answer for y dash would be minus x. I think I've got the correct quadrant now, because my point x dash y dash is now y comma minus x, y positive, x positive. So this is a positive number, minus of x is going to be negative. I seem to have got a point in the fourth quadrant, which is correct. So one possible combination of x dash and y dash is y comma minus x. So if this point is indeed y comma minus x, then the vector OP dash bar is going to be y I cap minus x j cap. Remember, x and y are the coordinates of P, whereas y and minus x are the coordinates of P dash, right? So OP dash bar is equal to y I cap minus x j cap. It's a vector in the proper direction. We want the direction of u cap, remember, but it's not a unit vector, so I have to divide it by its own magnitude, and then I get the unit vector in the proper direction. It's going to be root of y square plus x square. I can write it this way too, root of x square plus y square. That's the unit vector u cap in the proper direction which I wanted. And now all I have to do is to take this answer for the magnitude of b bar and multiply it by this unit vector. So my answer is going to be, I think I'll write it here, b bar is mu naught into I divided by 2 pi into, now the denominator contains a root x square plus y square, both in mod of b bar as well as in the unit vector, so this becomes x square plus y square, and what remains in the numerator is this term over here. So I multiplied by y I cap minus x j cap, and this is going to be the precise expression for the magnetic field at the point x comma y comma 0. So with this problem we complete this particular screencast lecture, and I just want to remind you, whatever we have done today you have to write in your classwork notebook. Thank you.